Back in in chapter 1, section 3, we just got over examining how to evaluate limits using the Epsilon-Delta definition. Now what we're going to do is we're going to approach it a little bit differently. We're going to use some properties that are, of course, proven by definition to help us evaluate limits analytically. All right, now it's important to remember that the limit of a function f of x as x approaches c does not depend on the value of your function at x equals c. It might not even be defined at x equals c. It's what happens as it approaches c. So it may turn out that the limit might be exactly what you would get if you substitute in, or it might not be that value at all. So in this case, we're going to also consider what happens when we can use direct substitution, which is perhaps the easiest method to evaluate a limit. Okay, when we can plug it straight in and use direct substitution, we get the limit as x goes to c of f of x equals f of c. Now, this occurs when the functions are what we call well-behaved. Well-behaved typically means it's continuous, and it's also typically doesn't have any corner points or cusp. We consider those functions to be well-behaved. Now, we have some basic properties which we're going to mention here, and all these properties were proven by mathematicians using Epsilon-Delta Proofs. And it says here, if we let the numbers b and c be real numbers, and we let n be a positive integer, then the limit as x approaches c of the number b is just b. It doesn't matter. It's like a horizontal line, y equals b. It doesn't matter if you approach it from the left or the right. You have the same y value at b. And in this case, the limit as x approaches c of x is equal to c. Now here's an example where we use direct substitution. We just plug the c right in for the variable and we get c. Here's another example of direct substitution. The limit as x approaches c of x to the n is equal to c to the n. So these are really nice ways to evaluate limits. There's no table, there's no graph, there's no definition, epsilon delta definition, which you guys may remember can be kind of rigorous. Now, here are three examples using these three properties. What is the limit as x approaches 5 of 9? Well, that's this guy right here, because this is a constant. So it doesn't matter if x approaches 5, if x approaches 10, if x approaches a million. The limit of 9 is going to be 9. Okay? And over here it says, what's the limit as x approaches 5 of x? Well, that's right here. We just use the direct substitution, plug 5 in, and we get 5. And in this case, it says, what's the limit as x approaches 5 of x raised to the power of 2? Well, that's this guy right here, and we just use direct substitution here as well, and we get 5 squared, or 25. So those are some of the most basic properties, and as you can see, evaluating the limit is very quick, very efficient. Now, here's some more properties that we're going to use. And these properties of limits are in this theorem. It says let b and c be real numbers, let n be a positive integer, just like we had in the previous properties. But in this case also, we're going to let f and g be functions with the following limits, that the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is K. So we have the 5 following properties here. The scalar multiple says that if you have the limit as x approaches c of a scalar, b, remember, is a real number, times some function, it's as if we just take the b, bring it out in front, and multiply it times the limit as x approaches c of f of x, which we already have, is L. So it's just b times the L. And some are different. These two make up what we call the linearity properties. It says that the limit as x approaches c of f of x plus or minus g of x is equal to as if the limit of f of x plus or minus the limit of g of x, L plus or minus k. Same thing, very similar here for products, quotients, and powers. The limit as x approaches c of f of x times g of x. It's as if we just take the limit as x approaches c of f of x times the limit as x approaches c of g of x, L times k. Here we have the limit as x approaches c of f of x over g of x is equal to L over k. Now, this, of course, is assuming that k cannot equal 0, because you can't have 0 in the denominator. And the power here, as x approaches c, the limit as x approaches c of f of x, and that function is raised to a power of n, is equal to the limit as x approaches c of f of x, all of that raised to the power of n, or L to the n. Now these properties, we don't necessarily say, oh, I'm going to use the scalar multiple property or I'm going to use the product property, but these are properties that we use all the time when we evaluate limits using this direct substitution, because as you can see, all of these are pretty much setting up, well, I shouldn't say direct substitution. All of these are setting up the fact that we have the limits given, and as I can show you before, that we use direct substitution there. So let's try a couple of examples here. Okay, this first one here, this is equal to, now notice I have a sum, so this is equal to the limit as x approaches 3 of the first part of the sum, the first term, plus the limit as x approaches 3 of the second part. Now, here's where it gets fun. This guy here, notice the 3, I can pop the 3 out in front, so this is 3 times the limit as x approaches 3 of x to the third, plus the limit as x approaches 3 of 5. And you'll notice now that I can go back to my basic function properties, the second one and the third one here, actually the first one. Oh, there goes my phone, of course. Sorry about that. All right. Lauren, I'm in the middle of a video, so I'm going to see what you need real quick. Hurry. Yes. Fine when I left, okay? Fine when I left, okay? I got to get back to, I'm right in the middle of the video and I don't know how to edit these, so this is stuck in my video. Okay, I'll let you go. Okay, bye-bye. Bye-bye. Sorry about that. That's what happens when you work with your daughter. All right, so in this case, this guy here is going to be using property number 3, which says that we can use direct substitution to plug it in. And the second part is going to be, since it's a constant, it's going to be using property number 1 here. So this part here, I'm going to use direct substitution. I didn't give myself very much room here. This 3 right here, this scalar multiple, and this is going to be 3 to the third, plus, and then this is just going to be 5. So this is 27 times 3 is 81 plus 5 is 86, and there's my limit. Now, you look at this and you say, Mr. Turner, do I have to separate it and do I have to pop the scalar out? Couldn't I just use direct substitution right into here and then of course use the property 1 there? Absolutely you could. As you can see, it's going to give you the same value. I'm just showing you how this works because of the properties that we do now have. Now this guy here looks really different because it's got a tangent function, but remember what tangent is. Tangent is the sine of x over the cosine of x. And of course that's all over x now. So what I'm going to do is I'm going to rewrite this. I'm going to write this as the limit as x goes to 0. I'm going to write this as the sine of x times 1 over the cosine of x. That's this part right here. Now, remember, this is like x over 1, so I'm going to invert and multiply, and I'm going to write this as 1 over x. Now, take a second to look at that, and you say, well, that's kind of strange. I don't think you're helping yourself here. Absolutely I am. Because now I'm going to multiply these two together, and I'm going to write this as the limit as x goes to 0 of the sine of x over x times 1 over the cosine of x. And I have a product. So if I use my property on product and write this as a product of limits, I get the limit, equals, I get the limit as x goes to 0 of the sine of x all over x times the limit as x goes to 0 of 1 over the cosine of x. Now the limit as x goes to 0 of the sine of x over x, this is one of our special trig limits, this is equal to 1. And here I can use direct substitution because in this case the cosine of x, the cosine of 0 is 1, so this is 1 times 1, and all this is equal to 1. Interesting. Now here's some more theorems that we're going to look at to help us along the with evaluating limits here. And of course we're looking for as many opportunities to use direct substitution as we can. So the first theorem says that if we have the limit of a polynomial or a rational function. Now remember, polynomial functions and rational functions where they're defined are well-behaved functions. And because they're well-behaved, we're going to be able to use the direct substitution approach. If p is a polynomial function and c is an element of the real numbers, then the limit as x approaches c of p of x, notice direct substitution p of c. If r is a rational function given by the fact that r of x is equal to p of x over q of x, where p of x and q of x are both polynomial functions, remember both polynomials, well behaved, and c is an element of real numbers such that q of c does not give me 0, I don't want 0 in the denominator, because that would be the denominator, then the limit of as r approaches c of r of x is equal to r of c. Now, what that allows us to do, again, for polynomials and for rational functions is to use this and get direct substitution as long as we don't get 0 in the denominator on the rationals. And here we have an example of a rational. The limit as x approaches 2 of x squared minus x minus 3 all over x plus 3. Well, if I use direct substitution here, if I plug 2 in, I am going to get 2 squared minus 2 minus 3 all over 2 plus 3. So this is going to give me 2 squared is 4, minus 2 is 2, minus 3 is negative 1, all over 5, and there's my limit. How easy is that? Much, much easier than going through the process of some epsilon-delta proof. I have an old epsilon-delta proof. I mentioned it before. I'll see if I can bring it in on the next video and show you how to do it the long way. But this is allowing us to use properties and theorems that were proven by mathematicians 200, 300, 400 years before we're around, and we are basically standing on the shoulders of giants to be able to see and be able to look ahead and be able to evaluate limits so conveniently. Next theorem up has to do with radicals. It says the limit of a function involving a radical. If n is a positive integer and the following limit is valid for all c if n is odd, because of course you have to be very careful when you have an odd, because the n is the index. When you have an odd index, okay, there's the other daughter. I'm not going to get through a complete video here. Hello, I'm right in the middle of a video. Everything okay? That's all right. Your sister interrupted about 5 minutes ago. I'm struggling to get through this one. Everything okay? Well, because it makes that silly sound, so I thought I'd better answer and make sure okay. I'm at school, but nope, I'll call you later. Okay, take care now. Thank you. Bye-bye. Well, that should be it. I had both daughters call, so the only one left to call will be the wife, and I don't think she's calling, but we'll see. All right, so anyway, if you have an odd indexed root, you have to be careful because you can have any value, because you can take the an odd root of a negative number. But if you have an even index root, then remember c is going to have to be greater than or equal to 0. And this says that the limit as x approaches c of the nth root of x is equal to the nth root of c. So again, direct substitution. Nice. And then even nicer, because most of our functions are composite functions, is the limit of a composite function. If f and g are functions such that the limit as x approaches c of g of x is equal to L, and the limit as x approaches L of f of x is equal to f of L, then the limit as x approaches c of this composite function f of g of x is equal to f of the limit as x approaches c of g of x, which we just said was L, and we get f of L. So again, what they're allowing us to do is to find the limit of the inside part here, because I have a composite function in this example. The outer function is the square root, the inner function is the polynomial. So first I find the limit of the polynomial part, and then I take the outer function of that. So if I plug 0 in, I get 0 squared plus 9, which is 9. So I get the square root of 9, which is equal to 3. All right. Now, trig functions, very similar as long as it's defined, as long as it's part of the domain of the trig function, because we know that there are 4 trig functions that have the variable in the denominator, and this just says direct substitution. Let c be an element of the real numbers in the domain of the given trig functions in the domain, and it says that as x approaches c, the sine of x is sine of c, cosine of x is cosine of c, tangent of x is tangent of c, and all the way through on all 6 trig functions. Very, very nice. Now we're going to use combinations of these properties to do some more limits here, and then we'll talk a little bit about strategy. All right, first guy up here, the limit as x approaches pi over 2 of x times the sine of x. Well, I'm telling you that this is the limit as x approaches pi over 2 of x times the limit as x approaches pi over 2 times the sine of x. Now, it's a good thing that you memorized that unit circle so that you can tell me what this value is. The limit as x approaches pi over 2 of x is pi over 2. That's from one of our basic properties, times the product property there. The limit as x approaches pi over 2 of the sine of x is the sine of pi over 2. Direct substitution. So the sine of pi over 2 is 1. This is pi over 2 times 1, or just pi over 2. Hopefully you can see that okay. Next guy up. Let's just scoot this up just a little. There we go. Try to keep it even. All right, I have x approaches, the limit as x approaches 0 of the cosine squared of x. So this is a composite function. The inside function is the cosine of x. The outside function is raising it to the power. So I'm telling you that this is equal to the limit as x approaches 0 of the cosine of x squared. The limit as x approaches 0 of the cosine of x, well, the cosine of 0 is 1. So this is equal to 1 squared, which is just equal to 1. Much simpler way to approach these. Now it says, note that all these limit properties involve direct substitution. Well, what happens here if we try direct substitution? The limit as x approaches 1 of x minus 1 over x squared minus 1. If I use direct substitution, I would get 1 minus 1 over 1 squared minus 1. I would get 0 over 0. Now, I may have mentioned this before. I believe I have. 0 over 0 is what we call an indeterminate form. Now, this doesn't mean it's undefined. It means we can't determine what it is. So in calculus, when you have 0 in the denominator, it's not always undefined. And you'll get a little bit more of that as we go through this and when we get to L'Hopital's rule. Theorem. Functions that agree at all but one point. Now you say, well, what does that have to do with this guy? Well, I'm going to come back to him in just a second. You can see it's the same example. And I'm going to show you how you can find this because in this case, this example can be, this function can be rewritten into another function. It says, let C be an element of the real numbers, and let f of x equal g of x. These two functions are equal for all x except c, and an open interval containing c. Then the limit of g of x as x approaches c, I wrote it twice, I'm not sure why, exists. Then the limit of f of x also exists, and the limit of f as x approaches c of f of x is equal to the limit as x approaches c of g of x. What this is saying is if you have two functions that agree at every value except c, and that's the one that you're taking the limit of, if the limit exists for the one, it exists for the other, and they're the same. Now you say, well, why would that be important? Well, you may have already noticed that algebraically, the denominator factors. I have x minus 1 times x plus 1 on the bottom. And look right here. At x minus 1, those factors cancel top and bottom, so I get the limit as x approaches 1 of 1 over x plus 1. See, this function here and this function here are exactly the same. They're exactly the same at every value except at 1, because in this case 1 is undefined here. But now I can use direct substitution. This limit exists, and I get 1 over 1 plus 1. And of course, ever since kindergarten, 1 plus 1 is still 2, so I get 1/2, and that's my answer. All right, so there is a strategy to finding limits here. So this is what I usually refer to as applying a little bit of algebra to get to it. But there are limits that there is a strategy for finding limits, and we're best off if we can kind of follow it and just use a little common sense. The strategy is learn to recognize which limits can be evaluated by direct substitution. That's your polynomials, that's your rationals, things like that, your radicals. If the limit as x approaches c cannot be evaluated by direct substitution, then we try to use a little bit of algebra to find a function g that agrees with f, like I did here. How this function here and this function here agreed with one another for all values except that in this case the limit as x was approaching 1. That was where we were evaluating our limit. All right, then if we can do that, if we can do a little bit of algebra and simplify it, and I'm going to show you a couple of more examples here, but if we can do a little bit of algebra and simplify the function so that we can evaluate it, then that's great. We'll go ahead and we'll use this theorem right here. Now, if all else fails, then we go back to square one, And that is that we use a graph or we use a table of values to try to figure out what's going on. Now, this is also a way to make sure that our answers are agreeing if we are using step 1 or step 2 here, or strategy 1, strategy 2. But now here, for an example, we're evaluating the limit as x approaches 5. Well, you can see right away that I'm going to get 0 in the denominator if I use direct substitution. But just like the last example, I can do a little bit of algebra. This is x minus 5 times x plus 1 all over x minus 5. I can simplify this, and I have the limit as x approaches 5 of x plus 1. Well, the limit as x approaches 5 of x plus 1, I can use direct substitution. This function agrees with this function at every possible x except for 5. But as I mentioned before at the very beginning of this video, it doesn't have to, you don't even have to have our function defined at the value in which you're taking the limit of. So in this case, I'm just going to use direct substitution. I'm going to put 5 plus 1, which is 6. Now, if you're doing problems like this on an assignment, and you say, well, what kind of work do I show? Show the work like I'm showing you here. Go ahead and show me the algebra. Don't jump to an answer. Don't look at a graph on decimals and try to figure it out, or go to some website that'll find you the limit, and it doesn't show you why that's the limit. Show me the work that I can make sure that you understand what's going on. Now, this next example is a little bit more to it, and that is evaluate the limit as x approaches 0 of, in this case, this weird looking radical. I just realized that I think I may have said something wrong earlier, but I'm going to correct it when I get there in just 1 second. The limit as x approaches 0 of the square root of x plus 4 minus 2 all over x. Now, if I use direct substitution, I'd get the square root of 4 minus 2, which is 2 minus 2, or 0, all over 0, and that's indeterminate. So what I'm going to do instead here is I'm going to try to do some kind of algebra trick so that maybe I can get a function that agrees at every value of x except at 0. And the only trick that I can think of here is to multiply the numerator and the denominator by the conjugate of the numerator, the radical conjugate. All right, so that would give me the limit as x goes to 0 of the square root of x plus 4 minus 2 all over x, and I'm going to multiply the square root of x plus 4 plus 2 top and bottom. All right, so I'm going to multiply the numerator and the denominator top and bottom by that. I hope you'll see why in just a second. The numerator is going to simplify very nicely, and the denominator, this factor down here, is not going to give me 0 if I plug 0 in. So up top, it's kind of like a difference of squares. These are conjugates. So I'm going to get the limit as x approaches 0. Oops, my fingers are in the way here. The limit as x approaches 0 of, up top, I'm going to get x plus 4 minus 4 all over x times the quantity of the square root of x plus 4 plus 2. Do you see how the 4's cancel? That's nice. I get the limit as x approaches 0 of x all over x times the quantity of the square root of x plus 4 plus 2. Well, look at the x's top and bottom. Those are the guys that were giving me 0 top and bottom. So now I have the limit as x goes to 0 of 1 all over the square root of x plus 4. That's a 4 there. All that plus 2. Now if I use direct substitution, my numerator is 1. And my denominator turns out to be the square root of 4, which is 2, plus 2. I end up with 1/4. All right, you will see this type of problem. This is a classic type of limit that AP people love to throw into like a multiple choice problem on the test. Now, I mentioned earlier that the limit as x approaches 0 of the sine of x all over x was equal to 1. And I said it was a special trig limit. Well, actually, here are my special trig limits, and you can see that is one of them. But we did evaluate that using a table of values back, I think it was in the previous section. So what I'm going to do here is I'm going to just make mention of what we call the Squeeze Theorem or the Sandwich Theorem, which is the theorem that is used to show that this limit here does indeed exist and is equal to 1. All right, the Squeeze Theorem, which I don't think will pop up on the AP test, but you never know. So it's worthwhile to make note of it. It says if k of x is less than f of x is less than or equal to g of x for all x, remember this means for all x in an open interval containing c, except possibly c itself, and if the limit as x approaches c of h of x is equal to L, which is equal to the limit as x approaches c of g of x, the outside functions, if they both have a limit as x goes to c of L, then the limit of the middle function as x goes to c exists and is also equal to L. I kind of like to think of seeing how it's kind of like squeezed or sandwiched in between these two functions. Both of these functions are having a limit of L as x approaches c, so the middle one is forced to have it, kind of like it's caught between a rock and a hard spot. It's forced to have the same limit. And that's the limit that's proven here that you can show. In fact, I think in the textbook they actually prove this using the Squeeze Theorem. And here's another key theorem, and this is one that you ought to memorize. These both you ought to memorize. And that is the limit as x approaches 0 of 1 minus the cosine of x over x is also equal to 0. Now, if you use direct substitution, you get 0 over 0. That's indeterminate. So you think, well, how do I get 0 for that? Well, you get 0 from that from a proof using the Squeeze Theorem. Now, I have a couple of examples that are typical of problems that you will see that uses this special trig limit. I think probably out of these two, this one is used a little bit more often, and that's why I have both examples like this. It says the limit as x approaches 0 of the sine of 2x over x. Now, this is not exactly the same because this is sine of x over x. This is sine of 2x over x. So what I'm going to do here is I'm going to take the limit as x approaches 0, and I'm going to rewrite this. I'm going to multiply top and bottom here by 2. So I get 2 the sine of 2x all over 2x. And then I'm going to bring this constant, this scalar out in front. I'm going to write this as 2 times the limit as x approaches 0 of the sine of 2x over 2x. Now, notice how these match. These match here. Remember this guy, how they matched right here? But it was as x goes to 0. Now think about it. If x goes to 0, what's happening to 2x? It's also going to go to 0. So this is the same as saying the limit as 2x goes to 0 of the sine of 2x over 2x. And if you want to, you could actually put a variable substitution. Call this u, call this u, call this u, and then you use exactly this first special trig limit. So this is equal to 2 times 1, or it's equal to 2. Kind of wild. This guy over here, a little bit easier. You've got the sine of x, but you have a 5x here. So what I'm going to do is I'm going to think of this as the sine of x over x, and the 5 I'm going to think of as 1/5 times that. Because if I multiply the numerators and denominators, I get right back to where I started. And since this is a constant, I can bring them out in front. I can write this as 1/5 times the limit as x approaches 0 over the sine of x over x, which is this guy right here. This guy right here is equal to 1. So this is 1/5 times 1, which is 1/5. It's going to take a little bit of practice to get good at this. So make sure that you try enough problems that you can determine whether or not this is sinking in, and so that you can find limits, because you will be asked to find limits on the AP test.